Pluto, a former planet that was renamed as a dwarf planet, remains a subject of interest in the vast universe. According to ongoing conjectures by leading subject matter experts, Pluto's orbit is hazardously near Neptune's. Astrophysicists Neil deGrasse Tyson and Kaku are both raising the alarm about a potentially dangerous mishap between these two planets, which could imply a massive liability to Earth. However, how is such an event even conceivable? Pluto's journey around the Sun is dissimilar to that of any other planet in our solar system. It requires a stunning 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. Anyway, the interest doesn't stop there. Pluto's orbit is marked by its especially curved shape, wandering broadly from the almost round orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, 17 degrees to the ecliptic plane. The way Pluto follows its path is significantly more unpredictable compared to other planets. This inclination and irregularity add layers of intricacy to its orbital plan. Possibly one of the most fascinating pieces of Pluto's orbit is its convergence with Neptune's. For around 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This prompts the usual inquiry, why hasn't Pluto crashed into Neptune? The assessment of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and erratic shape. The mystery grew with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, notwithstanding these complexities, is proof of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects in space like Pluto, Neptune, and the Sun move and impact each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. For Pluto's situation, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complicated manner. The terms asynchronous vibration, orbital precession, and VZK wobbling are key to this riddle, as explained by astrophysicists. Asynchronous vibration essentially means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial division is crucial in keeping their orbits from meeting. Orbital precession, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. VZK wobbling, named after three scientists Zell, Kai, and Kaku, studies how objects move in space. It involves how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. For Pluto's case, the VZK wobbling helps us understand why its orbit near the Sun is so irregular. Despite Pluto's orbit seeming tumultuous, this wobbling helps keep it moving smoothly over stretch periods. The VZK wobbling shows that despite things in space seeming wild and unusual, patterns and rules maintain some control. These forces help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or veer off course. This three-body problem is key to understanding how these orbits change due to the way space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite the stabilizing properties, Pluto's orbit is actually irregular, with minor deviations in initial conditions leading to massive differences over hundreds of years. However, these characteristics of Pluto's orbit have been found to maintain stability over incredibly long time scales. Checking the disturbances from later automated assessments has helped us understand how the giant planets like Neptune, Jupiter, and Saturn impact Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune is not alone at work. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn too contributes. These studies show that Jupiter's immense gravity is strong enough to ensure Pluto stays on a steady path for quite a while, possibly even for a very long period of time. So perhaps Neptune, Jupiter, and Saturn are coordinating to ensure Pluto continues to move safely through space without running into trouble. These peculiarities are crucial for keeping everything in place. Without these mechanisms, the solar system, as we know, it would be a much rougher place. Bodies like Pluto could crash into others or be ejected from their steady orbits, setting off a chain reaction with other celestial bodies. For Pluto, particularly with concerns about it possibly crashing into Neptune in the future, understanding its orbit is essential. This gives a clearer picture of the dynamic nature of the nearby solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and analysis of these peculiarities to better understand our place in the universe.